as I mentioned in class, we would be doing vectors remotely or via the flipped classroom model. So I left room here in the notes packet for these terms, which we actually defined in class today. But one word that we didn't define is force. A very simple definition for a force is a push or a pull. Very simple, but it's important just to have a little definition before we get into vectors, because a force is a vector quantity. Again, that means it has magnitude and direction. And a force is going to be measured in what's called newtons. And we're going to do a lot with forces this year, I promise you that. So, moving forward, often vector quantities are represented by drawing an arrow above the variable symbol. I'm doing my best with handwriting here, but drawing an arrow above the symbol. So if we have acceleration, well, we just draw a little arrow above that to represent it. So vectors are always represented by an arrow. If you are representing a vector, you have to make sure it has an arrowhead on it. Otherwise, it is definitely not a vector. Okay, there's a lot, and I guess it is when we're really, drawing them and drawing them out, they should be drawn to scale. So it's important to note that. And we'll do an example with that in class next week. So conventions for measuring angles. In physics, you just have to always be very careful about what you're measuring and with respect to what. It's something called the reference frame, but conventions for measuring angles, again, I support tractors. So we need more tractors. I'm a protractor. So that's that. But conventions for measuring angles, they can be measured in a lot of different ways. So if we're talking about, we can measure it from X or Y axis. So if I have some coordinate plane here and I draw a vector like this, let's say that's my vector. I'm just going to make something up. Let's say that this angle here is 43 degrees. So 43 degrees. Now we could say that this vector is, again, here's the x-axis, here's the y. We could say it's 43 degrees above the x-axis. We could also say I personally wouldn't, but if you wanted to say, you could say 47 degrees. What that would be clockwise from the y-axis, and so on. You could also say 43 degrees counterclockwise from the x-axis or the positive x-axis, and so on. But a lot of times we'll just say with respect to the cardinal directions. So the cardinal directions, we have north, we have south, we have east, and we have west. So in this case, instead of, if I draw kind of a compass here, so I'm just going to draw it over, and this is north, never eat shredded wheat. Still remember that from 7th grade global or 7th grade social studies. But in this case, that vector, sorry, it's getting messy here, would be called 43 degrees north of east. We cannot just say, if we have something that's up and to the right, 45 degrees, unless the components are completely equal. So that's just another way to denote that. Very important, two vectors are equal if and only if. So we're going to have three reasons. The first one is if they have the same magnitude. Again, it's a vector. So if you want vectors, if you want vectors to be equal, they have to have the same direction. and number 3. Number 3 is the hardest one to get. They have to be measuring the same quantity. Moving right along, the negative of a vector just means opposite in direction. So if I have vector A over here, well, negative A would be drawn like that. Same magnitude, same exact size, but opposite direction. So scalar multiplication, again, now we're not changing the direction because that, remember with scalars we don't care about direction. But let's say vector A is 6 kilometers to the east. Well, if we do scalar multiplication and say vector 2A, well, that's going to be 12 kilometers to the east, and we still draw that represented with an arrow. Okay, so a bunch of different ways to do vectors, whether it's scale drawings, you could set up a big table and do a lot of trig, or we can do it analytically. But for now, let's just go into this first example. So we have an airplane flying east at 200 meters per second. For example A, when we want to know the velocity relative to the ground, there's a tailwind of 50 meters per second east. So that is going to be in the same direction as the plane. So we're going to add these up, and it's going to be 250 meters per second to the east. There's a headwind. Well, that's in the opposite direction. So that's going to slow us down. We're going to be going at 150 meters per second. Still to the east. So we should write that, because this is a vector quantity. So both of those are to the east. So if there's a crosswind that's going north, well, this, when they're in opposite directions, it's going to be a minimum and it's going to be a max. So if there's a crosswind, my magnitude's going to be in between 150 and 250 meters per second. We could do, say we have 200 meters per second, and the crosswind is going at 50 meters per second. Well, essentially what we're doing is creating a right triangle, and I'm going to go somewhere in the northeast direction. Not quite northeast, but somewhere in that direction. I have a nice right triangle where I can do trig, do Pythagorean theorem to find this resultant velocity. So the sum of two or more vectors is going to be called, this is vectors, the resultant. And the resultant is the single vector which can replace all other vectors acting on an object and still produce the same effect. The tip to tail or tail to tip method is how I usually draw vectors. I will show you something called the parallelogram method when we're in class. So I'm just going to jump right into the example. And you can leave some room there as well if you want, and we can do some more examples in class. But we place the tail of one. So if we have a vector with an arrow, the tip of the arrow, and we have the tail of the arrow. So that's just the vocab. So we place the tail of one vector at the tip of the other vector. And the resultant is drawn from the very tail of the first to the last vector that you draw. So if we have, let's say our first vector is in this direction, and then, I don't know, something like here. So this second vector, the tail is placed at the tip of the first. The resultant is from exactly where we started. Remember, we defined displacement today as the start point to the end point. So that displacement is going to be a resultant. So if we have vector A here and B here, the resultant is from where we started to where we ended. And you can have way more, I should put arrows, but you can have way more than just two vectors, as long as we're going from the start point to the end point. that would be our resultant vector. Okay, so here, like this is going off the same example. Drawing this tip to tail, we have 200, and really this should be to scale. I am not to scale right now. And 50 meters per second to the east. The resultant is from where we started to where we ended. You can see the same thing here. If we have 200, I should draw that a little bigger. So 200. But now the headwind is in the opposite direction. So the resultant is from where we started to where we ended. And you can see that that headwind will cause the resultant velocity to slow down. Okay, and then I want you to try this one on your own. We're also going to save this for class because we're going to do a nice scale drawing. Won't affect your homework. But I'll just help you set this up, and then you can solve it on your own. So if we have 3 kilometers east, start to finish, and again, you should know the hypotenuse based on what we said, but you need to add in a direction. So on Monday, I'm going to check and see if we got that direction. Okay, find the magnitude of the resultant for adding vectors in each of the following cases. So again, if we're in the same direction, so I'm going to do it over here, 5 kilometers east and 12 kilometers east, well, that's going to be 17 kilometers east. Now, if we have 5 kilometers east and 12 kilometers north, that's going to be a situation where we do Pythagorean theorem. So again, I like to draw a picture, but we'll have 5 and then 12. And again, this is another special right triangle, so I don't even have to do math. If I could draw a 5. So here's a right triangle. Here's the resultant. So B, that should be 13 kilometers, because that's a special right triangle. And then C, when they're in opposite directions, we subtract them. So 7 kilometers east and then 12 kilometers west. 5 minus 12, well, we're going to have 7 kilometers west or negative 7 kilometers. Either one of those are totally acceptable. Okay, and then 2 forces, magnitudes 3 newtons and 4 newtons are added. The resultant may have, so if we add these together in the same direction, the max that a 3 Newton vector and a 4 Newton vector can have is 7. And then the min, if we subtract them in their opposite directions, would be 4 minus 3. So the smallest resultant that these 2 vectors can produce is 1 Newton. So it says the resultant of these vectors may have a magnitude of. So my answer has to fall within between 1 and 7. So we can cross off 0, we can cross off this. Definitely can be 6, but it can't be 10. Say vector subtraction, a special case of vector addition. Well, basically, all I mean is we're still adding vectors. We're always going to add them together. But when we're talking about subtracting them, we're just changing the direction. So if we have vector A minus B, well, essentially that's like saying vector A plus the negative of vector B. So again, that will, the more examples we do, the clearer that we'll get. Let's say we have coordinate plane, and let's say this is my vector, and we'll call it again vector A. So how do we resolve it into components? Well, again, this is going to be the x-axis. This is going to be the y-axis. So we're going to have an x component. Probably I'm going to draw that a little better. An x component right there. So this is going to be ax, and a y component, which goes vertically. And again, we have a right triangle, so it's going to be ay. Call this angle theta. That's terrible theta. So resolving it into components. Now, we could easily just use trig and say the cosine of theta is equal to the adjacent, which is ax, over a. So then I can cross multiply, and I get a times the cosine of theta equals ax. And the same thing, ax. The same thing applies for ay. Well, the sine of theta, use a different color, is equal to opposite, which is ay over a. So the y component would be found by doing a times the sine of theta, and that equals ay. So a lot of different vectors will have these components. Here's an example. Again, if you looked at the plane example quickly, we could be pulling a crate, and so on. So here, we'll just quickly practice. We're going to save this. That's going to be our example where we draw to scale in class. So quickly, I'm going to do my best because these are kind of small. This will be the x. This will be the y. This is the x. Okay, so all of these vectors have different components. And then the equilibrant, that's going to be the single force which cancels out the effect of all forces acting on an object.